Okay, we've looked at the topic of vector spaces and subspaces, and then we talked about spanning sets. And what I want to talk about in section 4.3 here is, as the title states, linear independence. And the reason we need to talk about this is we're building our way towards the next section where we'll talk about what a basis is, and then from a basis we'll be able to define the dimension of a vector space. And so got a lot of terms that we'll be defining and then applying in the next few sections. So let's take a look at this first definition, which defines what we mean by linear independence. So if I have a set of vectors in a vector space, V, then that set of vectors, or the vectors themselves, are said to be linearly independent, or the set is a linearly independent set, if no vector in that set can be written as a linear combination of the other vectors in the set. Let that sink in for a minute. So no vector in the set can be written as a linear combination of the other vectors in the set. And we talked about linear combination last time. And so if a set is not linearly independent, then it's said to be linearly dependent. Now, I usually abbreviate linear independent. Sometimes you'll see me write that, L-I-N-I-N-D, for linearly independent, and linearly dependent that way. Just my notation. Now, show why the set of vectors S equal to these three vectors which reside in 3 space. These vectors are 3 space vectors. Let's show that this set is linearly dependent. Well, what must that mean if it's linearly dependent? If they're linearly independent, then we cannot write any one vector as a linear combination of the others. Therefore, if you're linearly dependent, it must be that at least one of the vectors can be written as a linear combination of the others. And I'm going to show you that right now. The vector 1, 0, negative 2, the first vector in this set right here, is equal to the vector 7, 2, 0 plus negative 2 times the vector 3, 1, 1. Now, just confirm that this indeed is true. All right? If I scalar multiply the vector 3, 1, 1, which is the second vector in the set, by negative 2, I get negative 6, negative 2, negative 2. And then I add 7 plus a negative 6. What's that? 1. 2 plus a negative 2, 0. 0 plus a negative 2, negative 2. So hopefully you can indeed agree that this is a true statement. Now, your question might be, how in the world did I come up with that? How did I just know to take one of these and then negative 2 times this? Well, I set this up so it'll work that way. But what I want to show you then is the fact that in this case, if it is possible to write one vector as a linear combination of the other two, it's called linearly dependent. Now, why might we call it linearly dependent? Well, the value of this vector, what? This vector, the value of this vector here, what? Depends upon the values of these other vectors. It's written as a linear combination of these other vectors, right? So it depends upon the values of this. And in fact, if you think about it, I could also write, for instance, the vector 7, 2, 0 as a linear combination of the other two by what? Simply adding 2 times this vector to both sides, and I can write 7, 2, 0 as 2 times 3, 1, 1 plus this vector here. And then I think you can also see how I can solve this for the vector 3, 1, 1. Right? And so each one of these vectors can be written as a linear combination of the others. They're dependent upon one another. If I change one of the vectors, that's going to affect the whole set, right? Because they're interconnected in a sense. Okay? If we can't do that, then does that make sense that they're linearly independent? Okay. Well, so hopefully that gives you a little understanding of what we mean. But when we actually are trying to determine whether a set is linearly independent or linearly dependent, it's typical not that we're going to just come up with this and relationship like this. Kind of hard, in general, just to say, hey, I can see if I take, one of negative 2 times this and one of these, I get this vector. So we're going to build a method to so that we can find or determine rather whether a set is linearly independent or not. And so what I want to do is in this case, if I can write one vector as a linear combination of the others, then it's always true I can do something like this, which is I'm going to subtract, if you will, this vector, right, or add -1 times that, if you will, to both sides, and then I'm going to add 2 times this one to both sides. And if I do that, what am I going to get? What's my answer going to be? It's going to be the 0 vector, right, which is 0, 0, 0, right? That's the 0 vector. In other words, I just, subtracted this vector basically and added, 2 times this one to both sides. So in other words, if I can write one vector as a linear combination of the others, then I can write them as a linear combination equal to the 0 vector. Okay? And I'll have you note in this case that if we do so, at least one of these vectors, right, the coefficient in front of it has to be non-zero, namely this one for sure, right? We know we've got 1 times this, right? I can't have 0 here. And this, what would be the case if these 3 vectors were linearly independent? If I couldn't write one as a linear combination of the others, well, if I had this linear combination of the vectors set equal to 0, the only way I wouldn't be able to solve for any one vector is if the coefficient in front of it was 0. Right? If there's a 0 here, there's a 0 here, and then there's 0 here, then I couldn't solve for one of the vectors in terms of the others. I'll have you note, though, if I have 0 here, and 0 here, and 0 here, this equation is still true. Right? If I take 0 times this vector, plus 0 times this vector, plus 0 times this vector, I get 0. Right? And so this is the idea behind the next sort of, not really a definition, but a way of determining whether a set is linearly independent. So what we're going to do is, if we have a set of vectors in a vector space, right, and we want to know if they're linearly independent, well, we're going to look at this equation. We're going to take each vector and form a linear combination of those vectors. Remember what that is, right? Well, these k1 through k2 are scalars, and we want to set them equal to the 0 vector. And when is the set of vectors going to be linearly independent? That's going to be true when only the trivial solution exists. In other words, only when k1, k2, all these coefficients are 0, which is obviously always true, is it not? If I let k1 be 0, k2 be 0, and all these coefficients be 0, I get 0. But notice the key here is it's the only solution, right? Only the trivial solution. All right, that's the key. In other words, if I can find a non-trivial solution where at least one of these values, at least one, all I need is at least one, k1, k2 through kr, if at least one of those is not 0, then those vectors must be linearly dependent. Because in the case if k1 is not 0, I can solve for v1 in terms of the other ones, right? I can solve for v1 in terms of the other one if k1 is not 0, right? Just subtract, if you will, all the other ones and then divide by or multiply by 1 over k1, right, the reciprocal. And I've solved for v1. So that's how we're going to determine linearly independence. Now, note that in a set with exactly 2 vectors, that set will be linearly independent what? If and only if what? They're not scalar multiples of each other. Right? They're not scalar multiples of each other. Does that make sense? If one was a scalar multiple of another, then you're writing one in terms of the other. It's dependent. There's dependence there, right? And so if one can be written as a scalar multiple of the other, then they're linearly dependent. If not, then they're going to be linearly independent. So, and just to illustrate that, suppose vector v1 is, say, 3 times vector v2. Say my 2 vectors are v1 and v2. Then notice right away that I can form v1 plus a -3 v2 equaling the 0 vector. Right? So again, you see the dependence, right? These are clearly linearly dependent. And again, you see we have a linear combination of the vectors set equal to the 0 vector. And there's a non-trivial solution for the k's, right? k1 is 1, k2 is -3. And so they must be linearly dependent. So that's, if you have just two vectors, then we'll simply say, is one a scalar multiple of the other, to determine whether or not they are linearly independent. So let's take a look at a situation with three vectors to see if they are linearly independent or not. And we'll stay in 3 space. We're comfortable with that vector space. We've used it quite a bit. And so, are these 3 vectors linearly independent? Okay. Now, if you can immediately see a way to combine, write one of these vectors in terms of the other two, then you would know that they're linearly dependent. Okay, but that's kind of hard proposition to think about. So, what are we going to do? We're going to take a linear combination of these 3 vectors, and set it equal to the 0 vector. Right? And the question is there only the trivial solution? If there's only the trivial solution, then they're linearly independent. If I can find one non-trivial solution, to find the value of K1, K2, or K3 where all 3 are not equal to 0, then they're linearly dependent. All right, so we've dealt with linear combinations before, all right, where we were trying to find out if we can write one vector as a linear combination of the others. We're just trying to see, can I write the 0 vector as a linear combination of these vectors? Of course, we know again that I always can if K1, K2, and K3 are 0, right? Obviously, if they're all 3 0, then the statement is true. The question is that the only solution? So to determine that, let me go ahead and scalar multiply K1 times V1, and I'll get K1, comma, what? 2K1, comma, negative K1, right? Distribute that K1 through. Scalar multiply V2 by K2. And then scalar multiply V3 by K3. 0 there, and negative 2K3 equals the 0 vector. What's the 0 vector in 3 space? It's that right there. And so this looks familiar, right? So when is this? When will this be true? If I combine by adding these 3 vectors, then this statement will be true if what? The first component is equal to 0. What's the first component of the sum of these 3 vectors? It's K1 plus a negative 5K2 plus 10K3. I get K1 plus a negative 5K2, or minus 5K2, plus 10K3 equals 0. 2K1 plus 10K2 plus 0, just leave a space there, equals what? 0. And then negative K1 minus 3K2 minus 2K3 equals 0. And what do we have? System of linear equations, right? And certainly I could solve this system, okay? But let me just say, first of all, so let's do this in different color here. I can write this as the system AX equals 0, notice, right? Where X is the unknowns, and the unknowns in this case are K1, K2, and K3, right? With A equal to what? The coefficient matrix. Do you see the coefficient matrix from this? 1, 2, negative 1. Going down here, the coefficients. Negative 5, 10, negative 3, 10, 0, negative 2. And we've seen this before, right? I mean, when we think of matrix multiplication, AX, right, multiplying a matrix times the vector X is the same as taking a linear combination of what? The columns of the matrix A. And you can see the columns form what? Our corresponding vectors, right? 1, 2, negative 1, 1, 2, negative 1, negative 5, 10, negative 3, negative 5, 10, negative 3, 10, 0, negative 2, 10, 0, negative 2. Okay, so we're seeing this pattern. But again, it's really helpful, I think. Sometimes students will just throw a determinant down. They'll just start sliding these vectors in, but sometimes they put them in as rows instead of columns. They get all confused. So really, if you need to understand what's going on here, this is the key. And you really want to set this up and then write your system of linear equations out, and then get your matrix here. Now, What are we asked to find out? We want to know, are there non-trivial solutions? This is a homogeneous system. It's always consistent. Again, the trivial solution, where K1, K2, and K3 are all 0, is always a solution. The question is, are there no non-trivial solutions? Well, we can answer that question. In this case, we can answer it one way, is the fact that A is a square matrix. We know something about equivalent statements involving square matrices, right? AX equals 0, if A is a square matrix, this has only the trivial solution. If and only if what? If and only if what? Do you remember? If and only if A is what? Invertible. All right, remember the list of equivalent statements that we have? And what else is equivalent to A being invertible? If and only if what? The determinant of A is what? Not equal to 0, right? So these are all equivalent. So AX equals 0 has only the trivial solution if and only if the determinant of A is not 0. Determinant of A is not 0. Okay? However, what is the determinant of A? Well, using the calculator, I can find the determinant of this matrix, and I encourage you to do that. Right? And you're going to see the determinant is indeed 0. So what does that mean? If the determinant is not 0, then AX equals 0 has only the trivial solution. But the determinant of A is equal to 0, and so what must be true? There must be at least one non-trivial solution. There is at least one solution where not all of K1, K2, and K3 are all 0. And that means what? Going back to the original equation here, there's a non-trivial solution to this equation, which means that these are not linearly independent. They are linearly dependent. Right? And that comes from this analysis we've done below. So let's just sort of indicate that by saying, once we say this, we now know that's true. Okay, so these are vectors are linearly dependent. And that means what? One of these vectors, any one of these vectors, can be written as a linear combination of the others. Well, let's say at least, well, in this case all three can be, but in general at least one can be, we know. Now, could you do that? Could you write one as a linear combination of the others? Yeah, you could, and we could have determined the linear dependence another way, and that is, you know, what if this matrix A was not square? Then I wouldn't be able to do any of this. I mean, can I have a coefficient matrix that's not square? Yeah, you can have more equations than unknowns or more unknowns than equations. So this doesn't always work. However, I can always do what? I can always just solve this. Right? I can solve this system. How would I solve? So this would be another way. Let's do this in a different color. Let's say, or we can just solve. Right? Or just solve. And how would I solve? I would look at what? The augmented matrix. Which is what? Our coefficient matrix. And that includes, right, our constants, which are all zeros. There's our augmented matrix. And what would we do? We would do Gauss-Jordan elimination, right? Do all our row operations and get this to be in what form? Into reduced row echelon form, right? So I'm going to use technology to do that. And when I do so, here's what I get. Now, what's this tell us, right? So we have our unknowns. These are the coefficients of K1, K2, and K3. So we have a leading one here, K1 and K2 are fixed variables. K3 is what? Free. K3 is a free variable, so K3 is a parameter. So what does it mean in this case? Remember, we have a homogeneous system of linear equations. Therefore, we know the system is consistent. We always have the trivial solution. So it's a consistent system. And what does this tell me here? Because I have one parameter. This tells me I have infinitely many solutions. And what's that mean? It means I have non-trivial solutions. And if I have non-trivial solutions, then we reach the same conclusion we did here, right? Namely, that these vectors are linearly dependent. Okay? Now, I was saying you can now write, say, V1 in terms of the other two vectors. So how would you do that? Well, you can actually, I didn't actually solve the system. I said solve it. I really didn't. I just said there's infinitely many solutions. Do you remember how we solved this system? Right? We could solve by saying what? Let K3 be a parameter like T. And then what do we have from the first equation up there? K1, 1K1, 0K2 plus 5K3 equals 0. And so I can solve for K1. Our fixed variable is what? Negative 5T. And K2, second equation, minus K3 is 0. And so K2, add K3 is equal to K3, which is T. Right? And so from this, we can say what? The solution is, right, K1 is, well, negative 5T. I don't know why I'm rewriting this, but I am. K2 is T, and K3 is T. Okay, so you can now find a particular solution. Obviously, when T is 0, they're all 0, but that's not the one I want. I want a non-trivial one. So let T be something other than 0. I mean, like I can let it be 1. If T equals 1, then I've got negative 5, 1, and 1. And now I can come back up here. So K1 is negative 5, K2 is 1, K3 is 1. I can come back up here and write negative 5, right? V1, K1 is 5, negative 5, 1 for K2 plus V2 plus V3. Now you can solve for any one of these three vectors in terms of the others. Does that make sense? So you can do that. And there's really an infinite number of different ways you can do that based on the value of T you choose down here. Okay. Let's look at one more example. Are the vectors u1, u2, and u3 linearly independent? Okay, let's do this one a little quicker. Notice these vectors reside in 4 space, right? They're 4 tuples. Do you see that? As opposed to 3 tuples. But the process is the same. We take a linear combination of the vectors. Right? And I'm going to let you do this. You should see that this is going to this yields a system of linear equations with how many equations are we going to have and how many unknowns? How many equations, how many unknowns? Okay, remember what our unknowns were? What were we looking for? The unknowns are what? K1, the K2, and K3, these coefficients. Right? Again, we know K1, K2, and K3, all 0 is a solution. Right? We always have the trivial solution, right? The way we got this set up because it's equal to the 0 vector. And the question, are there non-trivial solutions? So we're looking for the values of K1, K2, and K3. So there's 3 unknowns. How many equations? Think about the last example, what we did there. Remember how I got each equation? And how did I get this equation here? It was by what? Looking at the first component values and setting them equal, right? Then the second, and then the third. And that's why I've got 3 equations, because they were ordered triples we're dealing with. Here we're dealing with what? Ordered 4 tuples. So we're going to have 4 equations in the 3 unknowns. And I'm going to go right to the augmented matrix to solve the system. So I'm going to let you see if you can come up with this augmented matrix. Again, you'll plug in U1, U2, U3, you'll distribute the K1, K2, and K3, and then you'll equate the first components, set them equal to 0, you'll add the second components, set them equal to 0, and that will give you your 4 equations in the 3 unknowns. And then when you write the augmented matrix, this is what you'll see. So I would definitely make sure that you go through and practice how to get this. Make sure you're very clear. Okay. Now, here's my augmented matrix. Hey, this is a 4 by 4 matrix, isn't it? It's a square matrix. Hey, could we just take the determinant of this matrix? Well, you certainly can. It's 4 by 4. What are you going to get if you take the determinant of this matrix? Without using any calculator, you should know the answer to that. What's the determinant of this matrix going to be? I hope you said 0. Why is it going to be 0? We've got a column of zeros, right? If I do cofactor expansion along this column, I'm going to get 0 for the determinant. Okay. So what's that tell us? Seems like in the last one, we got the determinant of 0 in the last one. That means that these are linearly dependent, right? No. Be very careful. Taking the determinant of the augmented matrix is not going to tell you anything. In fact, for any homogeneous system, the determinant of the augmented matrix will be 0 because you always have these zeros. Don't just get in the habit of just, well, let me just take a determinant. I've got a matrix. I don't know. Let's see what happens. Okay? What we're trying to do is solve this system. So what I want to do is not take the determinant of it. I want to put it in reduced row echelon form. I want to solve this system. And when I do so, I get this. And what does this tell me? What's this tell me? What's my solution? Do I have one solution, no solution, or infinitely many solutions? Well, I can't have no solution. We already know the trivial solution is there, right? It's a homogeneous system. Right? And I've got coefficients of K1, coefficients of K2, coefficients of K3. I've got 3 leading ones, or 1 in each column, right? There's no parameters, no free variables. They're all fixed. There's exactly one solution. The first equation says K1 plus 0, K2 plus 0, K3 equals 0, right? K1 equals 0. Second one says what? K2 equals 0. Third one says K3 equals 0. There's one solution. And of course, it's the trivial solution only, right? So trivial solution only. And we knew we had the trivial solution. We're just proving that it's trivial solution only, right? That's the important thing, that it's only the trivial solution. Therefore, what do we know about these vectors? Are they linearly independent? Yes. They are linearly independent. Okay? All right, we'll stop now, and we'll in the next video we'll take a little bit more look at this idea, and then look at a set of vectors in a different vector space and see if we can determine if they're linearly independent.